So yeah, VSEPR is the theory that is going to help us predict those shapes. We'll talk a little bit about hybrid orbitals and how the shapes are accounted for by orbitals sort of mixing together. And then we're going to talk about forces between molecules. So not just forces inside the molecules, but also forces that molecules have between one another. And also go into polyatomic ions with the idea of VSEPR theory. So molecular geometry determines some of the properties of molecules. It's going to tell us, for instance, if they're polar or not. Polarity has a lot to do with whether things dissolve or not, which is why water alone doesn't always dissolve everything. Like when you're doing laundry or dishes, you usually use some kind of soap because it's going to be something that's non-polar to sort of team up with the water, which is polar, because polar things tend to dissolve each other. Non-polar things tend to dissolve each other. So, molecular polarity, again, influences those forces that act between molecules for that reason, and you don't really get that information from just the chemical formula. So here we have two molecules. We have hydrogen, H2 molecule, and an HCl molecule, hydrogen chloride. We are looking at these because they only contain two atoms. They both have what's called a linear shape. Anytime you have two atoms bonded, just like in geometry, when you have 2 points, what's really the only shape you can make between 2 points? A straight line, right? So when we have two atoms, it's always going to be a straight line between them to make our molecule. The difference between these, though, is that notice hydrogen, if we were playing tug of war, you've got two equally matched challengers. They're going to pull on the bond equally. They're going to share those electrons very equally. Remember, we talked about ionic versus covalent. This would be a non-polar covalent bond. I'm going to write that out to remind us. This is going to be non-polar. Whereas on the other hand, you have the chlorine is much more electronegative than hydrogen. So we're going to have a little uneven match for the hydrogen chloride. In that case, we have a polar bond. So for linear shapes, we know it's nonpolar if the two atoms connected are equal or very similar in terms of electronegativity. So what does VSEPR stand for? It's valence shell electron pair repulsion. And that says that when we have these electrons surrounding an atom, it's going to cause them to want to be as far apart as possible. So like I said, we're going to talk about beryllium today, combined with two fluorine atoms. If beryllium is surrounded by two fluorine atoms, those fluorines on the end want to be as far apart as possible. If you were holding two things that needed to be as far apart as possible, you'd probably hold them, out at your sides 180 degrees apart from each other. So in a three-part molecule where there's no extra lone pairs or anything around the beryllium, there's only two bonds, that is going to be a linear shape. And I want to show you how to use those handouts that I gave you. Let's look at beryllium fluoride, BeF2. There's a link on Canvas. You can look at your VSEPR chart. And you see if I have, what I'm going to have to do is I'm going to have to choose a central atom. So in this case, the obvious choice is beryllium. How many, and we can either count pairs of electrons or bonds, so lone pairs or bonds. How many of those things are just around the beryllium? How many do you count there? Like how many bonds does beryllium have attached to it, basically? 2. So that's all I'm asking. The central atom, how many bonds are attached to it? Don't worry about all these lone pairs around the fluorine. Those don't matter for the shape of the molecule. Just look at the central atom, figure out how many things are around it, and that's where I'm looking on my chart. There's 2 total domains. In that case, it's either going to be 2 bonds like we see in beryllium fluoride, or it's going to be 1 bond and 1 lone pair. That's not the case, but either way it would be linear, and this is telling me my shape over here. So really what you're looking for is how many bonded atoms are around the central atom and how many lone pairs are around the central atom. Good with that? So we'll look at a couple more examples throughout the slideshow here. There's also some other shapes we're going to look at. We have the idea that we would have a molecule with a central atom and you have 3 bonds around it. In that case, they're going to stay furthest apart by pointing to the corners of a triangle, making 120-degree angles between each other. Any of you ever played Tetris? No? Tetris is a game from Russia, I believe. And you're trying to stack sets of different shapes of blocks, basically, to try to eliminate lines. And if you notice, every block you're trying to stack, they all have how many squares? Oh, except that one only has 3. I don't know. Maybe some Tetris games have 3. But yeah, typically all these are going to have 4 blocks. I think it wouldn't be Tetris if you only had 3. But anyway. So tetra just means 4, basically. So when I say tetrahedron, I don't know if that helps you remember it, but tetra basically means 4. So if I have 4 molecules, just like the one we did on the homework, the CH4, then we're talking about a tetrahedral shape, tetrahedron, which would look something like this. This lightly shaded triangle-looking thing in 3D, that's a tetrahedron, so we're saying that each of the atoms would appear at each corner of the tetrahedron, the 4 corners. That just gives them the best chance to be as far away from each other as possible. So we have an example here, boron trichloride. Remember, boron is another one before carbon. It doesn't have to have an octet. It is satisfied without an octet. So boron would have 3 valence electrons. And each chlorine would have 7. So I think we can kind of see how this is going to work out, right? You've got 3 lone dots on the chlorines, 3 lone dots on the boron. So we're going to have boron in the middle, connected to each chlorine. And all the chlorines are surrounded by 6. So in order to predict the... Does that make sense how I drew that? In order to predict the shape, again, choose a central atom. In this case, we'll choose boron. How many domains or how many things are around the boron? I see, 1, 2, 3. There's no lone pairs. So only 3. Go back to Tetris. Actually, I want to look at not chlorate, but my VSEPR table. If I find 3 domains, it's either going to involve bonded atoms or lone pairs. I said all 3 involve bonds, right? There were no lone pairs. So it's going to look like this shape here, the trigonal planar. meaning it's all in a flat line. Like if I could set that down, all the atoms would be in the same plane as one another, and it would lay flat. So that's what a trigonal planar molecule would look like. And when we build these in the lab, you're going to see in 3D what each of these shapes represents. But that would be trigonal planar. Any questions on how we got trigonal planar on the chart? Like when I look at the chart? So you agree that we had only three domains. We didn't have a fourth, like lone pair. Oh, you're on the wrong side. Yeah, the second page, you're not going to find it there. So yeah, you're good now. Yes, the 3 domains. We are good. So here's another one. Here's one that almost, if we looked at the last one, boron trichloride, we might expect this to also be a trigonal planar. But there's one difference about this one. You guys see the difference in that molecule? What's different between? Well, there are no bonds, but we can draw them. We remember every 2. You're on the right track, by the way. But these all count as a bond, but there's one extra factor. Yeah, there's a lone pair. So we're going to have to take that into account. I have 3 bonds and 1 lone pair. So now instead of a planar shape, we're going to have a trigonal pyramid going on here. And the pyramid's going to kind of stand up a little bit because that fourth domain is going to kind of scare these 3 away a little bit. They're going to draw closer to each other to get away from that lone pair at the top. So that would be, again, trigonal pyramidal. I'm just going to write trig, pyramid. Yeah, we need Lewis structures, so like I said, we'll have more opportunities to look at those. And I did put the homework up early. Like from drawing them from scratch?
Yeah.
Gotcha. We have ammonia is like that too. NH3. I guess that's what we were talking about. Ammonia is a trigonal pyramid. But what I meant to say, water is actually also tetrahedral. You might be tempted to say that it's linear because when we draw it, it looks kind of linear. But we're looking at it in 3D. It's actually what's called a bent molecule. Because I have 4 domains, right? I have 2 lone pairs and 2 bonds. That is not a symmetrical tetrahedron shape. That actually is asymmetrical. And you see that if I have 4 domains with 2 lone pairs and 2 bonds, that's a bent shape. And you see it in the picture. Very important to realize that water is tetrahedral in shape, but it's bent because that is where the idea that water is polar comes from. It's very important to know water is polar. It's because if in the picture, the Lewis dot structure alone, you might be tempted to say it's nonpolar because it looks symmetric, but remember, in tetrahedral shapes, all 4 of those domains need to be the same or similar in electronegativity. As you can see here, this is just like the shapes you can see. The tetrahedron looks like that. This is a trigonal pyramid, so you have 107 degrees. And then in a bent shape, the bending is 105 degrees rather. Normally in a tetrahedron, we see that 109.5. The 300. 109.5 bond angle is actually less when we have those other lone pairs involved because of the how they repel the other electrons more than bonding pairs do. Excuse me. So here's just some other ones we looked at. Linear shape with the beryllium fluoride, trigonal planar with boron trifluoride, and then again the tetrahedral. You can see all those angles included. But remember, there are some expanded geometries, which you can see later on like the second page, which you were looking at. If we expand geometry, so we can have 5 domains is rare, but there are some atoms like sulfur, things that have that third energy level that can expand into the 3D orbital. They could technically have 5 domains, and you see all sorts of shapes we can have if that's the case. And then even 6, you see like an octahedral shape. But we also want to look at polyatomic ions. They're going to be similar to how we treat molecules. I do have that list of shapes in the notes as well. Basically the same idea that we were looking at on the chart I shared on Canvas. But I want to erase. I guess I can't erase it. I want to start this from scratch. Like I said, drawing Lewis structures isn't going away. We're going to revisit it. So let's predict CO2. Again, carbon is likely going to be my central atom, and I'm just going to bond it to each oxygen. I know that carbon has 4 valence electrons, and each oxygen has 6. Times 2 gives me 12. So I'm looking for a total of 16 valence electrons in this shape. 4 from the carbon and 12 from my 2 oxygens. So when I draw this, if I give everybody an octet, I'm looking at 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Way too many valence electrons when I only have 16 to work with. So anybody remember what I can do to solve that problem? Yeah, double bonds.
Now,
so let's.
I'm getting this one a lot more than whatever the other one was.
Oh, gotcha. So,
I like actually counting it out.
using the versus using the dot. I see what you're saying. The method using the dots. So yeah, I'm gonna take. Notice I took away 2 lone pairs and made a double bond. So now oxygen has an octet. Carbon does not have an octet. Or no, sorry, carbon does. There's nothing wrong with this. Everything has an octet. The only thing is now we have to match the valence electrons. So again, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's what's wrong with it. So I have to, again, let's get rid of 2 lone pairs to make a double bond. Now I have 2, 4, 6, 8, 10, 12, 14, 16. Checks out. Octet, octet, octet. Everybody's happy. So this is what carbon dioxide would look like. 2 double bonds around the carbon connected to the 2 oxygens. That's not even what they're asking. They're asking me for the shape. So I look at carbon. I see how many domains, by the way. Might be tempted to say 4. But yeah, each double bond only counts as 1 domain. Good job picking up on that. So I only have 2 domains. There's no lone pairs. So what shape are we looking at here? Yeah, linear. So we can also do polyatomic ions. So this is linear. Let's make a chlorate, which in your notes, be aware there's a typo. It says 3-, but it's ClO3 with a -1 charge is what it should be. So chlorine sounds like it's going to be in the middle. Attached to 3 oxygens. You don't usually see chlorine in the middle, but for this ion you will. Chlorine has 7 valence electrons. Each oxygen has 6 valence electrons times 3. So I have 18. Which tells me 25 valence electrons. And then this minus charge, what do you think? Should I make it 24 valence electrons or 26 valence electrons? Yeah. Extra electron means I have extra. Or negative charge means I have an extra electron. So let's go ahead and just make everybody happy. Octet, 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 octet. Count my electrons. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Love when it works out. Just got to remember to include the fact that it's negatively charged. So the polyatomic ions, we didn't do a whole lot yesterday. How do you feel about that? So I think we're going to wrap it up here just to find the shape. Domains around the central atom. I've got 4, right? And in this case, 4. So 4 domains. 3 of them are bonds, and 1 of them is 3 of them are bonds. 1 of them is a lone pair. So in this case, the T. Yeah, in this case, the trigonal pyramid. See what's next here real quick. Yeah, so that leaves us to talk a little bit about hybridization tomorrow.